In today's video, we're going to be discussing ionization energy in terms of Coulombs Law. So if you have not watched the Coulombs Law video, please go back and do that so you understand what F, Q1, Q2, and D are, alright, before you go through with watching this video. First thing we need to do is we need to define what ionization energy is. And there are actually two definitions that are equally valid, right? They just kind of approach the problem from a different angle. Ionization energy, as you might be able to see by breaking down the word, is the energy related to making an ion. So it's the energy required to remove an electron from an atom. You're always going to start with the atoms that are the least attracted to the nucleus. Sorry, the electrons that are least attracted to the nucleus, and those are the ones that are the farthest away. So, if we were to ionize lithium, the first ionization energy would be the energy required to remove this first electron. I now have Li plus 1. I have removed a single electron, this one, and now I only have 2 electrons left. The second ionization energy of lithium would be the amount of energy needed to remove the second electron. To give you lithium 2+, and then finally lithium's third ionization energy would be the amount of energy needed to remove that final electron. There can be no fourth ionization energy for lithium because there is no fourth electron to remove. But there are as many ionization energies as there are numbers of electrons. So, this is one way to think about the problem. Another way to think about the problem is that it is the energy required to increase charge of an atom by +1. Right? The amount of energy you need to go from lithium neutral to lithium plus to lithium plus 2 to plus 3. And ionization energy has several relationships. Let's go think through them using Coulombs Law. So, it is the energy required to remove an electron. What do you think that its relationship is going to be to the force of attraction? That's right, these are direct. If the electron is harder to remove, it's harder to remove because it is more attracted. If ionization energy goes up, it's because force of attraction also went up. What about atomic radius? This is inverse. If the electrons are on lower energy levels, then they're going to be harder to remove. So as the radius goes down, the ionization energy goes up. What about Zeff, effective nuclear charge? Well, if we compare lithium to fluorine, we would see that lithium has a Zeff of +1 and 2 energy levels. Fluorine has a Zeff of +7 and 2 energy levels. So that means that although they have the same number of energy levels, fluorine is pulling much more strongly on its electrons than lithium. And if you're pulling more strongly on your electrons, they're going to require more energy to remove. Now this last one, I do want to put a little bit of an asterisk here, right? The answer I give here is going to be with the exception of noble gases, so I will not be considering noble gases here. But for electronegativity, let's think. If it is really difficult for me to remove an electron, then it stands to reason that that electron has a strong force of attraction to the nucleus, which also probably means that electronegativity is high. If I compare lithium to fluorine, then the one with the higher ionization energy will be the more electronegative, in this case, fluorine. If I compare lithium to sodium, then I will see that lithium has a higher ionization energy and it is more electronegative than sodium. Thank you for tuning in, and for the final video, which is going to be coming soon, we're going to figure out how we can apply Coulombs Law to explain lattice energy.